assignment. And no questions, no. So,
I guess I have a question.
okay.
I don't know if you're gonna get to this today, but in the homework, we covered parallel
No
resistors.
questions.
It asked a couple questions on parallel resistors, and I was kind of curious, does parallel and resistors means that they're stacked on top of each other?
No.
Or does it mean they're in sequence?
No, exactly.
So the series is the parallel?
So actually, one of the goals today would be to recognize when resistors are connected in parallel, when they're in series, and when they're connected in no particular way. In some arbitrary fashion that is neither parallel nor series, which is most of the cases. That's one of the things that we have to do. Okay, is it time or not? Is it time to? Okay, let's see. Okay, exactly time. Got the class. So we also have to schedule a midterm. And this means that we have to advance faster with homework assignments, practice test problems. So before the midterm, I'm going to give at least one optional problem solving session. So people to have the opportunity to ask about practice test problems. So the practice test is quite a few problems there, but most of them are trivial. Most of them are a single line, but still we have to write that single line when it is needed. Okay. So let's see where we stand so far. So the important result for this chapter started with Ohm's law. Let's write Ohm's law. And let's talk about AC, DC circuits.
You have a question, Doug?
Yes.
They asked, will the problem solving session be recorded and emailed out?
So the problem solving session is going to be recorded. And emailed. I'll email the link. But at least some people have to be here in person in order to ask questions. I'm not going to solve problems if I'm not asked to solve a problem. Right? You have to ask for a problem, and this means that you have to, well, we can do it by Zoom, but preferably we can communicate in person also. So I have to figure out what time is going to be this problem solving sessions. And it is not easy because there is no one time when everybody is available during the business days, right? Up until 5 o'clock. But we're going to figure out at least some problem solving session. And again, it is your job to try, or at least to look at problems and bring them to solution. Now, you also have to go over the homework problems. And also, well, we're going to solve as many problems as you bring in. Don't forget that you have the option to write your own exam questions by bringing them here in class and saying, oh, this is a good problem. We're going to solve it. We're going to make it public to everybody. And that problem is going to be given in the midterm, even for the final. So this is to encourage people to look at this textbook, look at different textbooks, bring interesting problems in. Okay, so we started with Ohm's law, which one way to interpret Ohm's law is to say that the voltage across a resistor is equal to the resistance of that resistor multiplied by the current that flows through that resistor. Very simple expression, but it has multiple uses in multiple different contexts. Last time we started talking about the power dissipated in a circuit, or the power dissipated in a single resistor, let's say. And we said that the power in some dissipated in some DC circuit with a single resistor is equal to the voltage across that resistor multiplied by the current that flows to that resistor. And after that, we took this, and together with Ohm's law, we found two alternative expressions for the power dissipated in a resistor. So it can be calculated as the current squared multiplied by the resistance, or it can be calculated as voltage squared divided by the resistance. And we are using those three formulas because in different cases, only one of those formulas may work. So all of this was with respect to DC circuits, direct current. We want to be able to generalize those expressions for power, for example, and any other expression for the case when you have AC voltage, alternating current. And we started with standard alternating current that changes as a sine function, sine or cosine function in time. So the voltage oscillates back and forth like this, like a sine function. The function that describes this time dependence, the time dependence of the voltage as a function of time, is some maximum value V naught, which is right here. Here is the V naught. And also here, of course, with negative sign. Multiplied by sine of 2 pi, the frequency f multiplied by time. And we're talking about alternating current that changes like a sine function, because this is what is everywhere around us, right? We have the power outlet here on the wall is generating AC voltage with frequency. What is the frequency of the on the grid? The frequency on the grid, this number f. How many oscillations per second? I'm sure that you know.
It should be 60.
Of course, 60. In Europe, it is 50, but here the frequency is 60 hertz. This means that you have 60 oscillations like this one per second. So this means that on this diagram here, this time interval is how long? From here to here. 1/60th of a second. 1/60th of a second. This is the period of oscillations. Okay, well, so you have a simple circuit with AC voltage like this, and a single resistor with resistance R connected to it. Well, the voltage as a function of time is given. What should be the value of the current that is flowing here? The current is also going to be oscillating in magnitude and direction. And you can find that current by using Ohm's law, right? You just take Ohm's law and say that current is equal to voltage divided by resistance. Resistance has a constant value. Voltage changes as a function of time. Therefore, the current also has to change as a function of time. In other words, the current as a function of time is going to be V naught divided by this constant value of the resistance times sine of 2 pi frequency t. Yes. And of course, this ratio of amplitude of the voltage divided by the resistance, we call that amplitude of the current, of course. This is the amplitude of the current. And on the diagram here, the current basically is going to change in sync with the voltage, like this, right? So the red is the current, and of course here is the amplitude of the current I naught right here on the diagram. Okay. So now let's continue in this discussion. Let's figure out the power. How does the power change in time? Well, you have to multiply the voltage times the current. You have to multiply the white function with the red function, right? This function times this function is going to give you the power as a function of time. So you have power as a function of time is going to be voltage multiplied by current. Well, I probably should write it over there so to be able to use the same diagram. So power is voltage times current. So it is going to be V naught times I naught times sine, but one sine from the voltage, one sine from the current is going to give you sine squared of 2 pi ft. This. And on the diagram, this is going to look like this. Let's see, here is still the time, but now here you have the power, and you see that the power is going to oscillate like this. Now, when the current is in negative direction and the voltage is also negative, their product is still going to be positive. So the power is going to oscillate like this. The power consumption in your circuit is just going to be like this. So you see that this circuit consumes power all the time, but there are moments of time like this one and this one and this one and this one when the power consumption becomes zero. The question is, what is the average of this constantly changing power consumption? And look, averaging over time, you can do graphically very easily. So let's say you want to average over time for this time interval, for one period, let's say. And you do it by looking at the area under the function, under this oscillating function, and finding average value, the average right here, such that the area of the rectangle is equal to the area of the under the oscillating function. So you can do it graphically, probably playing with areas, but averaging over time can be also done analytically. So you basically have to average this function. Average of a constant V naught is the same constant. Average of a constant I naught is the same constant. Average of sine squared it can be shown using a little bit of calculus that average of sine squared is exactly equal to 1/2, average over a single period of time. In other words, the average power in that case is going to be V naught times I naught times 1/2. And look, it is desirable to express this formula by dividing this 1/2, spreading it equally between the voltage and the current. So you can write this as V naught divided by square root of 2 and I naught divided by square root of 2. So square root of 2 multiplied by square root of 2 is exactly 2. So this is valid equality. And the reason for that weird way of writing is because amplitude divided by square root of 2 is exactly what we call root mean squared. So this is root mean squared of the voltage times root mean squared of the current. RMS for short, and this is a standard notation used in your textbook, RMS value. In other words, a formula to keep in mind is that anything RMS value is equal to the amplitude of that thing divided by the square root of 2. The same thing for RMS value of the current. Yes.
Can you please explain again how you went from the 1/2 in the VO
Yeah, well,
to the square root of 2?
I represented 1/2 as 1 over square root of 2 times 1 over square root of 2.
Oh,
Right?
yes, I understand.
And yeah, this is algebra, and everybody should have million questions related with algebra. Algebra is a tricky science, right? It is, yeah.
Does the RMS also work with the
Current too.
resistance, or only with volts and current?
Well, you can use RMS value for any variable that changes like a sine function. And look, the reasoning for introducing this RMS value is very simple. Look at the voltage in a AC circuit. Half of the time the voltage is positive, the other half of the time the voltage is negative. So on average, the voltage is 0. If you average the sine function, the average is 0, right? We talked about that. And this 0 doesn't tell you anything useful. So in order to find the average of this voltage, you somehow have to get rid of this negative values of the voltage, and you get rid of the negative by squaring the voltage. So if you square the voltage, the negative becomes positive, right? And well, RMS stands for square. So square it. After that, take the average, take the mean. And to compensate for the fact that you have squared it, take square root. And this is how the expression root mean squared comes out. You squared, you found the mean, and after that, you took square root. This is the idea behind the process. So for the voltage that comes, the voltage on the grid, what is the voltage that we have on this outlet here? We said that yes on Monday.
120.
120 volts. Is it average or amplitude?
The max, wouldn't it?
Actually, it is RMS. So the RMS value of the voltage is 120. The voltage amplitude, this maximum value is V RMS multiplied by square root of 2. And VRMS we say is 120. Square root of 2, your calculator knows what it is. What is this number? 120 times square root of 2.
It should be divided by, I think.
Yeah. Yeah, no, that's fine. Right? Look, RMS is amplitude divided by square root of 2. We said RMS is 120. Right.
69.7.
Okay, let's make it 170 approximately. So if you take an oscilloscope and you measure the maximum value, you are going to get that the maximum value of the voltage is 170 volts here.
So RMS represents the average voltage or the amplitude, or are those the same thing?
So V naught is amplitude,
Okay.
RMS is something like average. We said the average is 0, but 0 doesn't give you an idea what actually the voltage is. So in order to, RMS is something close to average, but not exactly average, because for a sine function, the average of a sine function is 0.
Thank you.
So the amplitude is 170 volt. Well, it changes by a few volts during the day, as when you have more consumption, usually the voltage drops, but the amplitude is around 170 and the RMS value is about 120. This is for the United States. In Europe, they have RMS value of 220, and amplitude is 220 times square root of 2, whatever that number is. Okay, so we're going to talk more about the voltage from the grid. I think that the last section in this chapter.
Why is it that when you use it more and you have less voltage?
So when you have multiple users, you actually, it is going to be a good thing actually if I try to answer this in a minute when I talk about parallel and series connections. So just give me a minute and we can do that. But basically, when too many people are using power, using energy, the power plant cannot provide all of the energy that is needed, and everybody gets cut by a little bit. This is how the voltage drops. But there is equipment that works well only when the voltage is exactly at the value that it has to be. And this is why, this is why we have, for devices like that need voltage that is fixed. Well, the laptop uses DC, but this device here makes sure that this DC value doesn't drop too much. It just weaken the, right? This converter makes sure that the device gets exactly what is needed. Okay, other remarks, questions? I'm a little bit puzzled that nobody is asking for homework questions.
haven't gotten to the parts that I talked about, that we talked about.
Like which problem?
Like, well, we finally, like, starting on number 3, we finally get to the average power. We just talked about that. So,
Okay.
and all that kind of stuff. So now we're finally getting to stuff that's on the homework.
Well, let's see. So let's go back to DC circuits. So we need, of course, some of those results, but I'm just going to copy the results like this. So we just got an expression for the power, average power in a DC circuit. So for a DC circuit, the average power is going to be calculated just by multiplying RMS values of the voltage and the current RMS values. Well, similarly, the second formula is going to be RMS value of the current squared, RMS squared times the resistance. Well, it became a little bit messy, so let's clean the diagrams, even though diagrams have the information, right? So you have current RMS squared times resistance, and this one is average power is equal to voltage RMS squared divided by the resistance. So you've got the idea here. Now let's go to a simple DC circuit. A circuit like this, you have a voltage provided, DC voltage provided by some batteries, but let's say that you have 2 resistors connected in the way it is shown here, resistor R1 and resistor R2. This type of connection of the 2 resistors is called connection in series. And the way to recognize it is by looking at the current that is flowing in this circuit. The current everywhere in this circuit is the same. So the same current flows through the first and through the second resistor. The same current everywhere in this circuit. This is how you recognize that 2 resistors are connected in series. The same current is flowing through them. Now, you can show with a little bit of algebra, which I'm going to, well, it is not given in the textbook, I'm not going to do it, but you can show that if you measure the voltage across the first resistor, and you're going to get some reading V1 for that voltage, and if you measure the voltage across the second resistor, and you measure voltage V2, what you can easily prove that the voltage provided by the battery is exactly going to be equal to the sum of the 2 voltage drops across the 2 resistors. Again, it is algebra, arithmetic, I'm skipping it, but this is an important result for devices, for resistors that are connected in series. If you had more resistors connected in series, maybe you had another one here, R3, you can add the voltage drop across the third resistor and so on. This is a universal result. You can interpret it, you can interpret this universal result by, well, look, you have a height difference between the 2 terminals of the battery, let's say a height difference of 5 meters. Well, you want, when you go through the loop, you want the height difference to be 5 meters. And you're going to encounter, well, no height, no any step here, But when you go through the first resistor, you're going to encounter one height step, maybe down. After that, another one, and after you go through this, you have to get to this 5 meters of height difference or 5 volts of voltage difference. You can easily write down algebraically, but let's not make the things more complicated they are. Just this result is important. Okay, now let's use this result the following way. The voltage across the first resistor, according to Ohm's law, should be equal to the current through that resistor multiplied by the resistance of that resistor. The same thing about the voltage across the second resistor. It is also going to be current times the value of the second resistance. And you can factor out the common factor of the current, and in the brackets you're going to have the sum of the two resistances. Call that sum of the two resistances as resistor RS. S stands for series. So the result that we got was that the voltage is equal to the current multiplied by RS, where RS is just the sum of the two resistances. And now if you look at another circuit with the same battery in it, but a resistor connected with a resistor with value RS, this second circuit behaves exactly like the previous one. In other words, the sum of the two resistors behaves like a single resistor with resistance RS if they're connected in series. So two resistors connected in series always can be replaced with a single resistor with value equal to the sum of the resistances, but only if they are connected in series. So clearly RS is larger than R1 and larger than R2. The resistances are always positive numbers. Any remarks so far? Now let's go to the second simple way of, before I go to the next topic, this result can be generalized for multiple resistors connected in series. So RS for multiple resistors is going to be R1 plus R2 plus R3 and so on, as many resistors you have, but they have to be, all of them have to be in series. The same current should flow through all of them. Yeah.
What is the resistance measured in?
In ohms.
Is that the same with the current?
So Ohm's law, if you look at Ohm's law and solve for resistance, is voltage divided by current. Voltage is measured in volts. The current is measured in amperes. And this ratio, volt per ampere, we call ohm. So volt per ampere is what we call ohm. And the standard notation is capital omega, Greek letter omega, capital omega. Okay, other remarks and questions? Now let's look at another way, another simple way to connect resistors or appliances in general. And that connection looks like this. You have again your battery. It could be also not a battery, but it could be AC power supply, but let's say a battery with voltage V, and you connect one resistor R1 this way, and the second resistor this way, the second resistor R2 this way. This is connection of two resistors or two appliances in parallel. But make no mistake, parallel connection doesn't mean that the two resistors are parallel to each other. Because exactly the same circuit, I can draw exactly the same circuit this way. Let's say this way. Here is the first resistor, and here I can draw the second resistor. This is exactly the same circuit, no difference whatsoever. But we still say, even though the two resistors are drawn perpendicular, this is still a connection in parallel. How to recognize connection in parallel? The only way to recognize that two appliances, two resistors are connected in parallel is to see if they're under the same voltage. And look, they're exactly under the same voltage because this is the same potential like this because those points are connected with a wire, and this point has exactly the same potential as this one. In this case, both resistors are under the voltage V provided by the battery. But the rule is, if the voltage is the same, the two resistors must be in parallel. Well, let's follow the same procedure like before. The voltage across the first resistor is voltage V, the same. That voltage, now look what happens with the current though, the current that is flowing. The current that comes from the battery, current I, reaches this junction point and splits into two. One part of the current goes this way in this branch, I1. The second part of the current continues this way and goes to the second resistor, I2. The current is different in the two resistors in general. Well, you can say that since electric charges are conserved, you can say that the total current coming from the battery is equal to the sum of the two currents. Right? It splits into two, but nothing is lost. The current, according to Ohm's law, right? Current, according to Ohm's law, is equal to voltage divided by resistance. So the current I1 should be equal to the voltage across the first resistor divided by the resistance of that resistor. And the current that goes to the second resistor is again the voltage across the second resistor, but it is the same voltage divided by resistance, R2. And again, you can factor out the common factor of voltage. And in the brackets, you have 1 over R1 plus 1 over R2. The expression in the brackets has dimension of inverse resistance. And we call that expression inverse of resistance connected in parallel, 1 over RP. P stands for parallel. In other words, we say that the inverse of RP is equal to the sum of the inverse of R1 and R2 inverse. This means that the circuit that we're analyzing is equivalent to a circuit that contains a single resistor with resistance RP. And RP has to be calculated using this expression. Well, if you solve this expression for RP, you are going to get RP is equal to the sum, to the product of the two resistors divided by their sum, R1 plus R2. And this is more convenient when you're figuring out. So RP has to have the value of product divided by difference.
So
Now,
ask, what does the P stand for in the RFP?
the subscript P stands for parallel, connected in parallel, right? The two resistors we say are connected in parallel, and P stands for parallel. Now, if we can connect more resistors in parallel, we can put R3 here, and so on, multiple. In that case, you are going to have the inverse of R parallel is going to be equal to the sum of the inverses, 1 over R1 plus 1 over R2 plus 1 over R3, and so on. But this formula now is not going to work. The formula for parallel equals to product divided by sum is not going to work algebraically anymore. You have to do it step by step. And if we have a chance, we can do that in the examples. So in the memory bank, let's put the resistance of two resistors connected in parallel. That it is equal to the product divided by the sum. Notice that connection in parallel generates a resistance that is smaller than the resistance R1 and resistance R2. So you connect two in parallel, two resistors in parallel, the effective resistance of this combination is smaller than each of the resistances that you have connected. Okay, now let's see questions. So the last section, well, not the last section, but probably the more time-consuming section in chapter 20 is description and exercising the application of so-called Kirchhoff rules. And well, we have something like 7-8 minutes. This is not sufficient time to formulate and exercise those rules. So I'll leave that for Friday. And now let's do an exercise about this connection in series and connection in parallel. Do you have any request for homework problem, or I can use some other example?
Could you, well, now it makes sense, but maybe good to go over it still. Number 8.
Let me see what is problem number 8. Let me just check it out. And if we're ready to do it, we're going to do it.
If not, you could do number 7 or 8.
Let's start with, okay, let's start with those are good examples, both 7 and 8. The problem is that they're the same value of the resistance. Let's start with problem number 7. Let me project it, and you can share. Yeah, problem number 7, you can share it. Okay, so yeah, 7, 8, we have quite a few examples to calculate the equivalent resistance. What is happening? Okay, so they have a circuit. You see that circuit on the board. They give you 4 resistors connected in a weird manner. What is the current delivered by the battery? So what you have to do here is to recognize that to find the current that goes through the battery, you have to replace this system of 4 resistors with a single resistor. And here is how to do it. So let's start with what you have on the board. 1 resistor, a second one, like this. Oops, yeah, okay. Let's do it like this. And this way. And you have the battery, right? It is the same circuit. Each of the resistors has value R. Is this the, oh, it is a different, well, it is the same way, but let me not confuse you. Let me draw it exactly the way they have drawn it. Exactly that way. R and R. Okay, so when you look at this circuit, how can you tell me how this and this resistor are connected? In series, in parallel? And again, I'm trying to take you. Those 2 resistors that are in the oval are connected neither in parallel nor in series. They're in some arbitrary way. Yeah.
Didn't you say that if the voltage is the same, then the 2 resistors are?
Yeah, well, look, you're right. But look, if I had different values for the resistances, the voltage wouldn't be the same.
So say, for example, you have 255 in that top left one. And then you've got 250 in that bottom right one, they're no longer in parallel.
Well, both of them are going to be under the same voltage, so they are going to be in parallel.
Oh.
But this one and this one are not, right? If you have different numbers, the voltages are going to be quite different.
In this case where they do have the same voltage, would they actually be in parallel?
No, in this case, they're still not in parallel, even though, so this is why I was reluctant to start with this example, because all resistors are the same, and it means that all voltages are everywhere the same, and it's a mess. But if each resistor had different value, you were going to see that only the voltage across those 2 is the same. So only those 2 are connected in parallel, and only those 2 are also connected in parallel. So now this means that I can substitute those 2 with a single resistor. So each resistor here is 255. I can replace it with a single resistor that I calculate as a product divided by the sum. And if you do this arithmetic, 255 multiplied by 255 and divided by 255 plus 255, the result that you're going to get is going to be 127.5. 127.5 ohms for this oval, right? How do I know that it is like this? Well, use your calculator and let me know if you get a different number when you do multiplication divided by sum. Is this what you're getting or not? Or nobody's look, this is, if I don't write the things correctly, we're not going to get the right answer. Yeah, okay. The same story for the second set of two resistors. The same story. You can replace it with a single resistor with resistance 127.5. So the equivalent circuit would look like this, the same voltage. Now, the two resistors that you see are connected how? In series. So their equivalent resistance is the sum of those two, and the sum of those two is 225 ohms. So this is the equivalent circuit. The initial circuit is equivalent to this circuit with a single resistor with value of 255, right? 255. Right? The sum of 127.5 and 127.5 is 255. And now you can immediately say that the current that flows here is going to be the voltage divided by the resistance. So it is going to be, for my version, the voltage is 9 volts divided by the resistance of 255 is going to give you some number that you have to tell me. Can you do this division so we enter?
0.035.
0.035, and this is exactly the answer for this. Now, yeah, this is the answer for my version. Now, we have multiple questions of this type. So problem number 8 is the same question, but many of the questions that follow, well, some of the questions that follow, for example, question number, let's see, 19, problem number 19. In problem number 19, you have two batteries, 4 resistors connected in some weird way. And to solve problems like problem number 19, we have to formulate and exercise Kirchhoff rules, which is a set of 5-6 steps that you have to follow. It is like a checklist, but you have to follow it strictly, and it is going to give you a system of 2 equations that eventually have to be solved algebraically. So we're going to do this on Friday, which means that we may have to change the due date for this homework assignment for next week, but please work on those homework problems.
Explain number 8 for those of us who are.
Okay, for people that can stay, let's look at problem number 8.
Before we start that, did you ever set, they're still wondering if you ever set a date for the exam?
The date for the exam is not set, but it should be sometime next week. We have to talk about that. Okay.
You were afraid and you know it.
Okay.
Yeah, actually, this class,
Okay, so problem number 8. Well, so for problem number 8, probably the first circuit is more tricky to figure out. But look, you can combine those two, they are in series, and the circuit is going to look like this. R here, R here, and On this part, you're going to have 2R. Here, like this. And this is the second, right? Now, those three are connected in parallel, but it is easier to add them in pairs. In other words, combine those two. And well, now they're in parallel. So it is a product divided by the sum. Product is R times R. Divided by the sum is R plus R. This is exactly R divided by 2. Right? Those are in parallel. So product divided by sum. In other words, this circuit becomes equal to R divided by 2. And this one is 2R. 2R. R divided by 2 and 2R. Like this. If you want, like this. And now, again, product divided by the sum. So product of R divided by 2 times 2R divided by the sum, R divided by 2 plus 2R. So on top you have R squared. In the bottom you have 5 times R divided by 2. Right. In other words, this is equal to 2R divided by 5, 2/5. 2/5 R is the first equivalent resistance. 2/5. For the second one, look, 2R, but 2R and 2R are in parallel. So the second circuit has total resistance of R.
Because if I were to multiply the sums.
Yep. The sum of 2R times, the product of 2R and 2R divided by the sum.
Plus 2R.
Yeah. So the, okay.
You have some students online watching you do number 8.
Okay,
Just so you
okay.
know.
Okay, thank you. So the second circuit is total resistance of R. And now,
So the third one, does it only have one in parallel and then?
so no. So those three in series first. So the last circuit looks like this. So when you combine those three, you are going to have a circuit like this. This one R stays, but the other three become 3R. So this is the equivalent resistance of. So to add those two, you have to add them in parallel, and their sum is going to be product 3R times R divided by the sum 4R gives you 3/4 R. Right?
You just look at this like without doing the math and see that since B has two groups that are in series and in series makes it bigger, that will automatically be bigger than C since it only has one group that is in series, or do you have to do the math?
You have to do the math. You're really going to make a mistake if you don't do the math. It's very easy to make mistakes here. And now you just have to see which is larger, 3/4, 2/5, or 1. Right? This is what they want you to arrange them in order, right? In
Largest to smallest.
So it's B, C, A.
yeah. So the largest is B. The next one is the C. So B, C, A. Yeah. Okay.
Thank you.
Yeah.
See you, Brandon.
See ya.
Okay, guys. So we're going to end the